All right, so welcome back to OneClass again. My name is Joey. I'm going to be your chemistry teacher for the next session. So if you were just tuning in for the first time, again, thank you so much for watching. And tuning into the OneClass channel. Here at OneClass, what we're aiming to do is we provide kind of online free lessons and live streams and videos for kind of students at home. So these are topics covering from basically secondary level math to and chemistry towards the college and the university level as well. In this particular session of this hour, what we're going to do is we're going to focus more on grade 12 chemistry. So again, senior level chemistry, and we have about 10 questions to talk about these topics and concepts here. Again, my name is Joey. I'm going to be your chemistry teacher for the session. Again, I come from a background with a secondary school educator level. So again, I have my teachables are in chemistry and science, as well as in music. And I'm hoping to get my math teachable further down the road in September. So without further ado, let's get started on today's topics and questions for today. All right, so let's do this. Let's start off with our first question here. It says match the following. It says draw the appropriate labels to their respective targets. And I can't really see these guys here, so I'm going to have to maybe redraw it here for you all. So this is, I think I have lithium iodide here. This is CH3OH. I have methanol, I can't even see it, CH3. It's just, the font is kind of small here. CH2F2. And LiI plus H2O, and then basically I'm given basically these labels here. Let me see if I can enlarge it. I have H2 plus H2O plus H2O. I have dipole. I have dispersion forces. I have an ionic bond, hydrogen bonding, and finally, ion dipole. So basically what we're going to do is we're looking at this left section and this right section, and we're going to basically match these guys with these terms here. So maybe I'll create some sort of line here, and we can think about where do they belong in terms of which category would they belong in. So we draw kind of this out here. Oh, whoops, that's not what I meant to do. That's clearly, my lines are clearly bad here. So this would have been, this here was oh whoops, CH2F2. F2, this would have been LiI plus H2O here, and then I can erase this guy over here. Okay, so we have, let me rewrite this actually, it's kind of messy here. So CH3, right? CH3, and maybe rewrite this as CH3OH here, is methanol. Okay, so I have all these guys here. So take a moment to think about this question. Again, what would match these compounds here? So let's take a moment to think about this. Again, think about what are dipole. This is the concept of intermolecular forces. What are dipole forces? What's a dispersion force? What's an ionic bond? Hydrogen bonding and ion dipole. So think about these problems for a minute, and then we will take up our answer like so. Okay, so let's do this problem here. So so this is lithium iodide, right? So lithium iodide, again, this is lithium iodide. Lithium is a metal, iodine is a non-metal, which means this would make an ionic bond. So I would have to erase this, and my first answer for this problem here would be an ionic bond, right? This would be ionic bond. I have a metal and a non-metal. Good. Let's look at this one here. CH3OH, this one would not be dipole. This would be an example of hydrogen bonding. And how do I know it's hydrogen bonding? Well, if I were to draw out the chemical compound here, I have C, I have C bond O, bond H, C bond OH, and this is H, and H over here, right? So if I this is the chemical structure of methanol, and basically what I have here, this is O is bonded to this oxygen here, right? And this oxygen again has lone pairs here. This is an example of hydrogen bonding. This has a hydroxyl group at the end here, and this H bond is very attracted to this oxygen here. So this here is a concept of hydrogen bonding, right? Again, it's the strongest intermolecular forces besides an ionic bond. So this here was as an example of hydrogen bonding. That's good. Number 3, this is CH3CH3. This is an example of dispersion forces, right? This is London dispersion. And I erase this because I want to write this in red. This is London dispersion. And the only reason why is if I were to, again, draw out the chemical compound of CH3CH3, you're going to realize that I get something like this. There's no dipole moments here. There's no ions here. There's no hydrogen bonding. Therefore, the only forces that exist here are dispersion forces, right? Again, dispersion forces usually are just depends on the atomic size of the molecule, and basically it's just the electrostatic forces that exist in the molecule here. So these are dispersion forces because I don't have a dipole moment. CH2F2 here would be a dipole force, right? This here would be dipole, and the reason why it's dipole here is because I have a dipole moment between carbon and the fluorine here, right? So let me redraw this out for you as well. So again, I have a carbon bond to carbon. I have one carbon only. Bond. This is bond fluorine, and then bond H and bond H. There's a dipole moment between, again, the fluorine here is partial negative, very electronegative, which makes the carbon here partial positive, right? So then again, there's a dipole moment between these two guys and these two guys here. This is a dipole intermolecular force here. So CH2F2 would be an example of a dipole force. And finally, lithium iodide plus water would be our ion dipole, right? This here would be our ion dipole, because I have a polar molecule such as water. Water is a polar molecule, and again, I have a cation or an anion as an ion, which is lithium iodide here. So in this sense, we have a dipole, right? So for example, if I were to let me erase this part here for you. What I have here is if I had lithium iodide, and this dissociates, so lithium iodide we dissociate to lithium positive and iodine minus, right? And this here, as along with the with water, if I bond water here, again, this here has the ion dipole, right? This here was a positive charge here. And then my partial negatives would come from the oxygen here, right? My partial negatives. Again, I have this as an ion here and a dipole here. Therefore, this is an ion dipole intermolecular force. So this here would fill up my chart here, and let's see what they have here. Therefore, okay, so let me just scan this quickly. So they're just talking about dispersion forces, dipole, ion dipole, and hydrogen bonding. Dispersion are the weakest intermolecular force. That's good. At present, nonpolar molecule. CH3 is a nonpolar molecule. There are no dipole moments. Hydrogen bonding is the strongest intermolecular force and represents a special class. So it's hydrogen bonded to nitrogen, oxygen, or fluorine. In this case, it was bonded to oxygen. So this here is an example of hydrogen bonding. Ion dipole is simply just a dissolution of an ionic molecule, so lithium and iodide, in a polar solvent such as water. And then we have the major forces coming into play when an ionic molecule is dissolved in a polar molecule, right? So again, I have a cation of lithium, and it's attracted to my dipole of oxygen here. That's good. And finally, dipole is simply just a dipole moment within the molecule here. So therefore, lithium iodide is our ionic bond, good. Hydrogen bonding is in methanol. CH3 is dispersion forces. CH2 is dipole forces, and lithium iodide in water is ion dipole. So this here is the correct answer, and they provided a great solution for all of these guys here. So this here solution is correct. Great analysis. Solution here is correct. Sweet, that's number 1. I don't think I wrote number 1 here. It's number 1. Okay, let's look at number 2. Number 2, which metal could you use to reduce manganese ions but not magnesium 2+ ions? So metal to reduce Mn. I'm guessing it's a positive Mn ions, but not magnesium 2+ ions. So this is talking about the concept of reduction, right? And let me just bring out a periodic table for you as well, so we can look at these guys here. So we have manganese, which is here is 25, and magnesium is 12, right? So let me just write that down for you. Manganese has an atomic number of 25, and this here is 12, right? So magnesium is again an alkaline earth metal, and manganese is actually it's part of the transition metals here. So let's see, which metal could you use to reduce Mn+ ions but not magnesium 2+, right? So in this case, when we're talking about reduction, remember oxidation is loss of electrons, is reduction, and oxidation, and reduction is gain of electrons, right? So when we're saying, I use the acronym LEO for loss of electrons equals oxidation. LEO says GER. GER is gain electrons, would be reduction, right? So we're talking about what metal to reduce these ions here. We are gaining electrons. So we're trying to get rid of this 2+ and the positive charge here. So let me just find out what the charge of manganese is, because I'm not quite sure. Manganese ion should be 2+ and I believe 4, or 2, 3, and 5, I believe. It's a transition metal, so it's a multivalent compound here. So just give me a second. Oxidation states. So it's 2+, 3+, 4+, 6+, and 7+. So there's a lot of oxidation states of manganese here. So it's just a multivalent compound here. So it says again, metal to reduce, or I think I spelled reduce here. Reduce manganese ions, but not magnesium ions. Would actually not exist, right? If you think about this question here, a metal here, I want to reduce want to reduce manganese, but not magnesium here. In order for me, if I look in terms of my periodic table, my magnesium is here, right? If I'm reducing a magnesium, if I want to only reduce manganese, I would reduce basically also every other metal that exists before manganese, such as magnesium, right? So in this case, when we talk about a metal that reduces manganese ions, but not magnesium ions, this doesn't exist. I could do the other way around, and I could pick a metal that only reduces magnesium, but not manganese, but I can't do the opposite because manganese is further down the periodic table. So let me see their explanation here. It says determine the metal that can be used to reduce, but not is to be stated. I don't know what that means. The metal that can be used to reduce, but not is aluminum. So it says here the explanation is the metal that can be used to reduce manganese must be a stronger reducing agent than manganese itself, right? That's good. That same metal cannot reduce magnesium metal, therefore that metal will be a weaker reducing agent than magnesium. From table 19.1, I don't have this table here. The metal that has the most negative value of standard reduction potential will be the strongest reducing agent, right? And it says here, it is observed that the reduction potential value for aluminum is more negative than for manganese. Therefore, aluminum can reduce manganese. However, aluminum can also so it says, therefore, aluminum can reduce manganese. Also, the reduction potential for aluminum is less negative for magnesium. Therefore, aluminum cannot reduce magnesium. So let me just search up this. This is the reduction potential table. So let me see what this. And in this chart, you're actually given this chart on your exam. So this is totally fine. And I'm looking for manganese here. So manganese, this is Mn plus E plus 1 electron gives me Mn2+. So this is a reduction of manganese, and I have a reduction for magnesium. Let me see where magnesium would be. There's another manganese dioxide here. But let me see if I can control find Mg. There we go. Mg here is 2 plus, right? 2 plus would be magnesium. This is the reduction of magnesium. Has a reduction value of negative 2.37. So let me just write this down here. So it's negative 2.37. Negative 2.37 is my reduction potential for the magnesium. And then for manganese, I have, sorry, I don't want my bookmark. I want manganese is here. I have a couple of them here, right? Let's take maybe, they're all basically above the half cell reaction. So they all have positive value here. And this is standard reduction potentials, right? So basically, let me take the worst case scenario, and we have maybe, let's do this one here, 1.23, the lowest one here, 1.23. This is positive 1.23. So as you can see, the reduction potential of manganese is much greater than the reduction potential of magnesium, right? So therefore, what I can say is I have to pick a metal on this table. So in this case, they picked aluminum. Aluminum has then a value of negative 1.6, so the reduction of aluminum is negative 1.66. So therefore, this one, so aluminum has a reduction potential of negative 1.66. So therefore, because aluminum has the reduction potential is smaller than manganese, this would actually reduce manganese, but it cannot reduce magnesium here because magnesium has a lower reduction potential. You could also pick basically anything. Titanium would be a metal, would be an acceptable answer for this one as well. Chromium would be an acceptable answer here. Zinc is another answer here. Gallium, iron, cadmium, nickel, all of these guys here would also do the exact same trick to reduce manganese, but not magnesium. So it really depends on which one you pick. The concept here is basically that if I was given a reduction potential table and you're given this on a test, and manganese reduction standard potentials, basically manganese, I have manganese would be this is positive 1.23. And then magnesium here is negative 2.37. Basically, any metal that exists between these 2 points can reduce manganese, but not magnesium. If I were to pick one that is lower than magnesium, it would reduce both of these metals here. So that's the topic of reduction here, reduction standard potentials. So again, they picked aluminum here, but you could pick something like zinc or cadmium or something like that. These are all acceptable metals for us to reduce manganese, but not magnesium. So there's a lot of correct answers for this solution here. So great solution. So wish that you attached whatever table 19.1 is for standard reduction potentials. But aluminum would be an acceptable answer to reduce manganese, but not magnesium. So it honestly really depends on the table, and you're given this table basically on the test here. So that's number 2. That's good. Let's look at number 3. So it says, which species is diamagnetic? And it says, so I'm looking at diamagnetic. And I have here, this is chromium 2 plus. I have B is zinc, C is manganese, and D is carbon. So it's talking about which species is diamagnetic. So when we're talking about this concept of being diamagnetic, we have to talk about this topic of electron configuration, right? So this topic of electron configuration, again, comes back in terms of where are the electrons and how do we know if it's diamagnetic or not. So let's draw out our electron configuration for all of these guys here to see whether or not they contain this diamagnetic property here. So take a moment to think about what the electron configuration is. I'm going to write it down here as well. So I'll bring up the periodic table for you to find out. Again, we're starting with chromium 2 plus here. Let's take a moment to think about this problem here. So again, we're thinking about the electron configurations first, and then what we can do is we can we can talk about which species are indeed diamagnetic. Okay, so let's look at the electron configuration for chromium. So when we talk about the electron configuration of chromium, I would have to find chromium on the periodic table, right? So this here is chromium, and I have to figure out the electron configuration. So I can say that before then I have, so it's 1s2, 2s2, 2p6, 3s2, 3p6, this is 4s2, and this would be 4 or 3D something, right? 1, 2, 3, 4. 3D4 here would be just the chromium chromium as an element. So let me just write down this. This is 4s2 3D4 would be just for chromium. However, I have a charge of 2 plus, right? So I'm losing 2 electrons from chromium here. So in this case, this would be, I would have to subtract 2 electrons to make a 2 plus charge, right? So I would have, this would be now 3D2. 3D2. Now, is this a diamagnetic series? In this case, it's not. It's not diamagnetic, and then in this case, this is paramagnetic. And the reason why is because this 3D shell is not filled. Therefore, it's paramagnetic and not diamagnetic. For it to be diamagnetic, I need my that orbitals need to be filled. So let's look at zinc here. So zinc here is this guy here. So this would be 4s2 and then 3D 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3D 10, right? So let me do this. Let me draw the electron configuration here. This is 4s2, 3D 10. And again, in this case, the 3D shell is filled, right? It has 10 electrons in my 3D 10 here. So this case, this zinc here is diamagnetic, right? The 3D shell is filled. I have 10 electrons in the shell here, which is great. Let's look at manganese to verify our answer. Manganese is here. Again, it's 4s2, 4, 1, 2, 4s2, 3D, 1, 2, 3, 4, and 5. This is 3D5, right? So I have, this is 4s2, 3D5. Again, this is only half filled. So in this case, because it's half filled, it's not diamagnetic. It's only paramagnetic. Can't say that word. 3D shell is not filled, or it's only half filled in this case. 3D shell is half filled. And finally, carbon, if I look at the electron configuration of 1s2, again, 2s2 here, and then 2p2 here, right? 2p2. So this would be 2s2, 2p2. And again, this here, the 2p shell is not filled. Therefore, it's not diamagnetic, which means B here is our correct answer. So let's look at the solution here. We're determining the diamagnetic series. So the answer is B. That's good. Zinc here. So a species containing one or more unpaired number of electrons is to be paramagnetic, right? So these are not filled. That's good. And the species only containing paired electrons only is to be diamagnetic. Di is again 2. Magnetic is just magnetic, right? So again, it has all the electrons are paired in this case, and it's filled in terms of the shell. So let's see. Chromium is electron configuration is something here. So they're missing the electron configuration. It has 4 unpaired electrons, right? That's good. Because if you draw out the 3D10 shell here, you realize that I have 1, 2, 3, 4, and 5. I only have 2 shells that are being filled here, right? So this here, the shell is not filled. That's good. So I have 4 unpaired electrons that are not filled. That's good. This is a paramagnetic species. That's good. Zinc here is 3d10, so it is diamagnetic. Manganese is half filled, 5 unpaired electrons. That's good. And finally, carbon here has 2 unpaired, right? So again, carbon as a 2p6 orbital. This is 2p. I only have 1 and 2, right? So again, I only have 2 electrons here, so therefore I have 2 unpaired electrons. I have 2 unpaired electrons in this case. So therefore, it's a paramagnetic species. So in this case, this solution is correct. Solution is correct. However, they are missing the electron configuration. Electron configuration of the elements here. So let me write this down. This is Cr2 plus base. I'm gonna use a shorthand here. So this is simply just 4s2. Or I'll actually use the shorthand here. So this is argon here. Argon. So it's argon first, and then it's 4s2. So argon is this, and it's 4s2, and then 3d2. So therefore, paramagnetic. This is Zn. This is zinc. Zinc here would give me again argon. I have 4s2. This is 3d10. Therefore, it is indeed diamagnetic. Diamagnetic. Manganese is again 4s2, so I can say argon again. This here is then 4s2 and 3d5. Sorry, 3d5. Therefore, paramagnetic. And then finally, carbon here has a 2s2 here, which is simply just 2s2 would be helium here. So this is, I guess I could write out 1s2. 1s2, 2s2. This is 2p, 2p2, right? 2p2 would be our last orbital here. That's good. Therefore, this would be paramagnetic. So therefore, the only answer in this case is zinc, because it has a 3D shell that is filled, right? Because 3D orbital is filled. Sweet. So the solution is correct there. We're just missing the electron configuration. The solution is correct. Sweet. Damon Wilson asks, can you teach me molecular mass? So I actually went through this topic of molecular mass already. I did this I did this on Tuesday, actually, the topic of molecular mass and molar mass. However, if you want me to I'll actually go through molar mass. Like if you want, I can do a super quick rundown. I'll literally do it now before I answer this question. So I'll teach you in like 2 minutes here. So if you're talking about molar mass, and Zachary says hi. Hi, Zachary. Molar mass or molecular mass is this topic of basically, if you know, in molar mass is you're given basically how much mass of it, how much the element weighs in terms of mass, so in terms of grams per basically a mole of a substance, right? A mole of a substance, and we know that a mole of a substance is. And we learned about kind of moles in your basically in your junior level chemistry course here. And grams per mole is simply just whatever the molecular mass is. So this is grams per mole is measured. That's kind of the units for molar mass. And basically you have grams per mole. So if you have 1 mole of a substance, 1 mole of a substance, and we know this because of Avogadro's number, right? It equals the Avogadro's number of atoms in that 1 mole of substance. So it's 6.02 times 10 to the power of 23 basically atoms per mole of a substance. So if I have 1 mole of carbon, I'm going to have 6.02 times 10 to the 23 atoms of that of carbon in that 1 mole. So if I say grams per mole, it's basically saying how much it weighs, right? How much that 1 mole substance weighs. So 1 mole of carbon weighs exactly, and we can look at the periodic table here, it exactly weighs 12.011, right? So that's how we determine the atomic mass here. And this is the molar mass, which is the molecular mass. So again, 12.011 would then equal, so if 1 mole of carbon atoms is equal to 6.02 times 10 to the 23 atoms of carbon, 1 mole of carbon, there will be basically this weighs 12.01 grams of carbon per mole of carbon. So that's kind of this topic of molar mass in like two kind of 2 seconds here. But what you can do is, if you're having trouble with molar mass, what you can do is, again, a formula that you really need to know in chemistry is moles equals mass over molar mass. And that simply just says moles equals mass, which is measured in grams, divided by molar mass, which is measured in grams per mole. So a lot of times what questions are asking is asking, oh, what is the molar mass of a specific question? What you can literally do is just go into the periodic table and add all those masses up to figure out your molar mass of the compound here. So I hope that helps, Damon, in terms of what this question is asking. This is more so grade 11 chemistry topic in terms of stoichiometry and moles and molar mass here. But I hope that helped. Again, I only taught in two minutes, so I hope that helped in terms of explaining this topic here. Sweet. So where was I? I was question 3. Then let's work on question 4. So question 4. Let's calculate the pH for each of the following cases in the titration of 50 milliliters of, this is HClO, so this is hypochlorite acid plus potassium hydroxide. The ionization constant for hypochlorite acid can be found. Where is I don't get the Ka here, which is weird, before addition of any potassium hydroxide at 25, after addition of 30, after 50, and after 60 here. No problem, David. Okay, so let's see here. Titration of 50 milliliters. Okay, so I have, let me just write out these constants here. So I have 50 milliliters of, this is 0.200 molars of, this is hypochlorite acid. And then I have with basically 0.20 molars of, this is KOH here. And this here is potassium hydroxide. So I simply have, this is a weak acid, strong base titration here, right? A hypochlorite acid here is a weak acid, and then I have a strong base. So classic titration here, classic weak acid, strong base titration. And then it says I have a ionization constant can be found. I don't know where that is. So I have to actually basically find out where that is. So let me just find that for you. So this is asking me, what is the ionization constant for HClO? Because I need to know that. So this is hypochlorous acid, sorry. It's hypochlorous acid. It's 2.81 times 10 to the negative 8 here. This is the Ka, right? Yes, negative 2.81 times 10 to the negative 8. So this is the Ka, which is 2.81 times 10 to the negative 8. And it says, okay, so it's asking us A, which is before addition of any KOH, right? So before we even add base, what is the pH of the solution here? So before we add base, so we only have acid. So let's say we only have 50 milliliters of our acid here. So in order for us to find out, we have to first write out our chemical formula, right? So we have HClO aqueous is going to dissolve in water, right? Water is our kind of solution here. It's going to dissolve in water. It's going to be in equilibrium. And what I'm going to get is I'm going to get H3O plus, which is our acid, plus ClO minus, which is our, this here would be our conjugate base here. So again, in this case, I have 50 milliliters of 0.200 molarity, which means my concentration of HClO is 0.200 molarity here. And what I can do is I can simply just use an ice table to figure out what the ionization constant, or with the ionization constant to find out what my concentration is. So I'm going to use an ice table. So let me just this is ice, and I basically use this for any equilibrium reaction, right? So initially I have 0.200 molars. The water in this case does not play a part, so I can throw an X in there. Initially I have 0 acid and 0 conjugate base. I'm going to subtract some sort of X here because I don't know how much is going in terms of how much acid I'm producing. I'm going to get some acid and some base, and therefore in the equilibrium I'm going to have 0.20 minus X. This will simply just be positive X and positive X here. So what I can do is now I can write my equilibrium expression, and I can say that it's going to be equal to 2.81 times 10 to the negative 8. 2.81 times 10 to the negative 8 will equal basically my products over my reactants, right? So in this case, it would be the concentration of H3O plus plus times the concentration of HClO minus would equal over this would be the concentration of hypochlorous acid, right? And again, water doesn't play a part in my concentrations here. Again, I can fill out that this here is 2.81 times 10 to the negative 8 equals, I have x times x, so I have x squared at the top. HClO is 0.200 minus x. I'm going to use the assumption method that this x is going to be super small to avoid using the quadratic formula, so I can simply just cross this out. I'm going to multiply both sides by 0.200. So let me just use my calculator here. I'm 2.81 times 10 to the negative 8 times 0.200. That's going to give me a value of 5.62 times 10 to the negative 9 equals x squared. I'm going to square root both sides to get x would finally equal 7.50 times 10 to the negative 5, and this would equal the concentration of my hydronium ion. And once I get that, I can simply just use, I'm going to do this in blue, I can simply just solve for the pH using, and am I solving for the pH? Oh, yeah, I'm right, calculate the pH. Negative log of the hydronium ion here. So negative log would equal basically 7.50 times 10 to the negative 5. In this case, negative log would then equal, the pH would then equal times 10 to the negative 5 would give me 4.12. So pH before we even add any base would be 4.12 here. So this here would be my solution for part A. So this is a lot of work to do part A, but basically you do the exact same thing for A, B, C, D, and E. So maybe I'll do one more, I'll maybe just do B, but basically you're repeating the same parts. So let me just check my answer real quick and see what if we verified our solution correctly. So part A is saying that they use exactly an ice table like I did as well. They drew out the ionization or the ionization reaction. That's perfect. And they use an ice table. They gave us the ionization constant is 3.0 times 10 to the negative 8. I wrote 2.81 here. So my answer might be different here, but it should be around, I have 4.12. This is 4.11. This here is basically the same thing. So this is exactly correct. They have the ice table here, x, and you have x squared. So you have x squared, and they use approximation method because k is very small. I use the exact same thing when I cross out this minus x here. I'm square rooting both sides for basically 5.6 times 10 to the power of 9, which I get 7.746. 7.50 is probably the same thing here. And then I use the negative log of the concentration of hydronium ions to figure out the pH, which is 4.12. This solution here is correct, so part A is correct here. So I'm going to just do one part. I'm just going to do basically the B for the sake of time because, again, I don't have that much time today. And this question is very long. So I'm just going to basically verify the solution here before we start. So let me just do part B for you, and then we will figure this out. Part B states that after adding 25 milliliters of base here. So I'm going to say that now I have 50 milliliters of 0.200 moles of hypochlorous acid, and then I added 25.0 milliliters of 0.200 molars of KOH. So now my titration has begun, right? I've added acid and some base, which is great. So now what I have to do first is I have to find out what the moles of these two things are before I find concentration. I'm going to have a new total volume, right? Because I'm going to add these two volumes together. So let me find the moles of HClO first. So moles of this would be simply concentration times the volume, right? If it's concentration equals N over V, then moles equals concentration times volume, right? So I have this would be equal to concentration, which is 0.200 times 0.05 liters, right? I changed 50 milliliters to liters here. This would get me a solution of 0.2 times 0.05 would give me 0.01. This here would be the moles of HClO. And finally, the moles of potassium hydroxide do the exact same thing. I have 0.200 moles. I'm multiplying it, however, by, this is 0.025 liters here. And then, sorry, that does not look like a 0. And then I'm going to get a solution which is 0.200 times 0.025 on my calculator. I get or get basically 5 times 10 to the negative 3 here. 5 times 10 to the negative 3 moles of KOH. So these are my moles of KOH here. Basically what I can do to these moles, I can divide it by the total volume, and the total volume in this case is 50 plus 25, right? So 50 plus 25 here is 75.0 milliliters is my total volume. So I have a new concentration of both my acid and my base, right? So I'm going to basically divide both of these guys by 0.075 liters to get my concentration of my acid and my base, right? So this here would be 0.01 divided by 0.075. 0.75, I would get a value of, this is 0.0133 molarity of, this is HClO, and this would be 0 or 5 times 10 to the negative 3 divided by 0.075, I would get 0.066 molarity here. So again, I have, these are my new concentrations for my for my ice table, basically, that I'm about to do here. And what I'm going to do is I'm going to do the exact same thing, figure out an ice table, and I'm going to figure out again what the concentration of my hydronium ions, so I can figure out my pH. So basically that's kind of the first step to figuring out what that is. Basically, I use these concentrations again, I draw my chemical formula, I do my ice table, and I'm going to solve for it. Again, for the sake of time, because I'm only on, this is what, question 4, I'm going to just simply just skip this step because I've already showed you how to do an ice table. So I'm going to just simply just verify the solution here for part B. And because again, this is a very, very long solution here. So again, they have here, this is HCl plus KOH is KClO plus H2O, that's good. And then what we have here is HClO plus hydroxide will give us our ClO minus an H2O, right? So this is our net ion equation, that's good. What they're doing is, again, they're solving for their moles like I did as well, 0.01 and 0.005. And then what they did was they're going to do an ice table to figure out which one's my limiting reagent. Again, my limiting reagent in this case would be, again, not my limiting reagent, sorry, I'm using my ice table. I have 0.01 as my acid and 0.05 as my base here. This will be the initial concentrations. I lose 0.05, I get 0 for my base here, and I get 0.005 for my acid, which means my X value would be 0.05. And simply what you can do then is you have basically the concentration of your HClO and equals the concentration of your ClO and H2O, right? So again, here at equilibrium, we have an acid and its conjugated base, ClO minus. Therefore, you can have a buffer system. And this is actually more so university level chem than grade 12 chem. Grade 12 chem would have actually probably got you to do the first part like I did, but because this is a buffer solution, because we have our acid and our conjugate base are exactly the same, pH would equal pKa. So the pKa is simply just negative log of our Ka value, which was 2.81, I believe it was 2.81 times 10 to the negative 8. If you do negative log of this number, you would get the pH after this here. This is at pH, this would be at the half equivalence point to figure out what this solution here is. So again, you can use the Henderson-Hasselbalch equation to figure out the buffer system, which is pH equals pKa, so P negative log of Ka of this, plus the concentration of base over acid. In this case, the ratio is 1, therefore pH equals pKa. So therefore, it's 7.52 when it's at half equivalence point. So this is more so a university level question, but when I was picking it, I picked the first part to show you kind of the ice table, which is part of the grade 12 kind of concepts here. I'm going to briefly skim over part C. Again, very similar to part C. You have, again, new moles here. Again, you have 40 milliliters instead of 25. You calculate, do the exact same thing in ice table, and then you do the exact same thing, Henderson-Hasselbalch equation, and you get a pH here, which looks pretty good to me. Yeah, the math checks out here. And then D here is you add 50 milliliters, you do the exact same thing, and you realize that in this case, you have reached equivalence point. Moles of acid equals moles of base. Therefore, you have 0 and 0 in terms of your initial acid base, which means you only have your products here. So in this case, your pH would be would be, let's see, let me see, pH of the solution is dependent on the concentration of the substance. So in this case, it's a pH of this would just be 0.01. So you can find the negative log of that to figure out your pH here. So pH when this is 50 milliliters. What they're doing here is they have, again, 0.01. Again, they're drawing the ice table here, but they realize that they've used up all their base, which means the only thing that's participating in our reaction is our ClO minus and ClO minus right here. So again, ClO minus, use minus some sort of X here, you get this Kb expression. And again, what you have here, or so you get a K expression here. And again, what we're doing here is we are solving for then our KB expression, because again now we're adding more base than acid here, so we want to use our KB. Therefore, we solve for our KB using kW, which is 1 times 10 to the negative 14, and then you solve for your KB, which is great. Then you could write out your equation for the dissociation constant. So again, ClO plus OH minus, the hydroxide ion over your ClO minus. That's good. And again, you have your ice table here. You substitute here. You get X equals 1.825, which is equal to a concentration of hydroxide ions. So now you can use PO power of hydroxide equals negative log of the hydroxide ion to get POH, and then you simply subtract 14 minus that to get your pH here. So again, this here is the exact same thing as part E here. So I'm going to say this solution is great. So this is actually a perfect solution here. Perfect solution. And answer. However, this solution is actually not that hard. Perfect solution and step-by-step analysis. So remember, we're doing the exact same thing, right? This question is simply just saying, oh, we have to find the moles of it first. Well, after we find the moles, we divide it by the total concentration, which is exactly the same here. After that, and then we're figuring out, okay, which one goes to which. We have our initial concentrations. We're going to subtract it by basically which one gets used up first, and that will be that we're going to make the conjugate acid and the conjugate base of that. We write out our dissociation constant. We've solved for X, which will be our concentration of our hydroxide ion, and then we simply just use pH equals negative log of our hydronium ions, not hydroxide, hydronium ions, to figure out pH. And we basically do that 4 times. But however, the moment we switch to adding more base than acid, we have passed our kind of equivalence point. We need to swap our Ka. So we have to actually rearrange algebraically to solve for our Kb, and then we do the exact same thing, but instead of solving for the hydronium ions, we're solving for hydroxide ions. And instead of solving for that, by solving for hydroxide ions, we can solve for our POH, which then we could convert to our pH by using 14 minus POH here. So this solution is correct. Whew, that was actually a really, really, really long answer. That was question 4, and now we're at question 5 here. Question 5 is an organic chemistry kind of question. So it says here, draw the products of the reactions here. So let's see. Of any reactions that take place. So I have cyclohexane, cyclohexanol, cyclohexanone, and benzaldehyde here. And basically, I'm reacting it with Br2 with a dichloro. This is dichloromethane here. So if I want to figure this out, I would have to simply just do. This would be a bromination reaction of cyclohexane here, but however, it's under CH2Cl2, right? So this here, dichloromethane, it's not going to, I have bromine under dichloromethane. This solvent is it's simply just a polar solvent for my bromine, right? In this case, it's actually not going to react because I have an alkane group. Again, if I want to chlorinate it, I need to use radical halogenation for me to get some type of reaction here. So in this case, hexane has no reaction with this one. It does not go through an oxidation reaction or a reduction reaction here. KMNO4 is an oxidation, is an oxidative oxidizing reagent, so it's not going to be reduced. CrO3 is chromium trioxide. This is a reduction. Oh no, this is also an oxidation. Sorry, also an oxidation reagent here, and then D24DNP would be our. Let me just see which this is. This is a Brady's reagent, I believe. and this would be to solve for your to get a nitro group into your it's basically just detects carbonyl functionality of a ketone or aldehyde group, and I believe it turns some specific color when you put it into that solution. I believe it's red or yellow. I think it's yellow. Let me just verify that. Just give me a second. A positive test is signaled, yeah, yellow, orange, or red precipitate. So you get dinitrophenyl hydrazone if you get a ketone or an aldehyde group here. So in this case here, cyclohexane does not mean anything. That's fine. But cyclohexene, it does. I do have a reaction, right? Cyclohexene with Br2 would give me simply just I'm adding towards the double bond, right? So this here with Br2 and CH2Cl2, I would get basically a bromination reaction. I get Br and Br here. So that would be, I would fill this out here. Again, CrO3, again, chromium trioxide, and KMNO4 would just be basically oxidation reactions here. And again, I don't have a alcohol group here. D4NP, again, I don't have a carbonyl group here, so I won't get a reaction here. So that's cyclohexene. Let's look at cyclohexanol. Cyclohexanol would be OH. If I react it with Br2, I will get no reaction. Again, the OH group is a tough leaving group. This is a very, very strong bond, and it will not leave. Br2 would not substitute OH, so would not get a reaction here. CrO3 over in the presence of acetone as its solvent would give me a oxidation reaction. It would give me an oxidation, and I would get a ketone, right? Same with if I were to use KMNO4, I would also get a ketone here. In this case, I wouldn't get a carboxylic acid because again, this alcohol here is a secondary alcohol. I cannot reduce secondary alcohols to carboxylic acid. So in this case, these two products would give me that. Again, with D4NP, DNP, again, I don't have a carbonyl group, which means I won't get some sort of product here, which is fine. And then finally, I have hexanone. Hexanone would not react with bromine. Again, I'm not substituting this O. Again, I can't oxidize this any further, so I don't get a reaction here. However, with D4-DNP, it will make a product, and again, it will make the red precipitate that we talked about here. So that's great. So D4-NP will make a reaction here. And finally, benzyl aldehyde. Again, Br2 will not substitute it. That's fine. CrO3, let me just check the strength of CrO3 for you real quick. Chromium trioxide. Is it enough to oxidize to a carboxylic acid? I know KMNO4 would be, because potassium permanganate is a very strong oxidizing reagent. Let me just check if it's a strong or again, it is a strong oxidizing reagent. So in this case, benzyl aldehyde would reduce to a oxidize to a carboxylic acid. So you get something like this. You would get OH, and this would basically oxidize. So I'm going to do an O here. This would be a benzene again, and then we get a carboxylic acid, like so. And then in the presence of D4-DNP, again, because I do have a carbonyl group, I will make my red and orange precipitate. So let me look at the answer here. And again, this is correct, right? Again, I don't get a reaction here. I even took it a step further, and I actually wrote out the products. Again, no reactions for alkanes like stated before. Br2, again, will definitely add to the double bond, like Br here and Br here. KMNO4 would react with the cyclohexene to oxidize. Let me just double check that. I believe that's true. Oxidizing alkenes. And I believe that it can basically cleave the bond, right? Let me just, you would basically, you wouldn't cleave the bond, but you would get, it would add a diol group. So let me just write this down for you. you have an alkene here, and if you react it with KMnO4, like a very, very strong oxidizing reagent, in this case, CrO3 would not do the same thing. This it's just a very, because KMnO4 again, it's basically the strongest oxidizing reagent. It's going to form a diol here. So I have OH here and OH here. So it will react with KMnO4, but not with CrO3. Cyclohexanol, again, I can oxidize both of these to make a ketone, so both these are correct. Hexanone, again, I would only get D4-DMP. There should be a check mark here. Again, I do get a colorless. It basically detects a carbonyl group, and this here, a ketone, is my carbonyl group, so that's good. And finally, benzaldehyde, I can oxidize both of these to become carboxylic acids, and it will become a red precipitate in D4-DMP. So this solution here is correct. This solution is correct. Again, CrO3 here only reacts with aldehydes and alcohols and not alkenes. It's just because KMnO4 is such a big, such a strong oxidizing reactions that they can actually produce a diol here. Solution is correct. Sweet. So let me see if I have. I don't know if I have time to do one more problem, but maybe I'll try. This would be number 6 here. Maybe I'll just verify this answer, and I won't do the side work here. But it says determine whether or not each metal, if coated into iron, would prevent the corrosion of iron. So again, I believe I've done this question before, or I've seen this as well. Cu. So if coated in iron, which is Fe, would it prevent the corrosion of iron? So if I coat magnesium onto iron, would it corrode? If I coat chromium into iron, would it corrode? And would I coat copper onto iron, would it corrode? Basically, you're looking at this point, when you're talking about corrosion, you're talking about this topic of oxidations, right? So basically what we have to do is we have to actually look at our oxidation potential tables and figure out if it has a greater oxidation potential than iron here. So let me see here. The metals that can be used as a sacrificial electrode to prevent the corrosion of iron are magnesium and chromium, right? So magnesium and chromium would prevent the corrosion of iron. But if coated, explanation corrosion is just simply oxidation. That's good. Basically, it's saying here, any metal that has a higher tendency to be oxidized than iron can be used as a sacrificial coating. So if you did look at our oxidation potential tables, you would see that magnesium and chromium have a higher tendency. So it's higher up, which means it will be oxidized first than iron, right? Whereas copper here is below the table, below iron in the oxidation potentials. Therefore, it will not protect would not protect against the corrosion of iron, because iron will corrode first before copper corrodes here. So this here solution is correct. Again, I'm looking for the value of standard electropotentials. So let me just let me Google that for you. Values of standard reduction potentials. Again, on a test given situation, you're given all these topics, right? So don't worry about trying to memorize these guys here. Like, you're given all of these guys here. This is the standard reduction potentials. Again, you have iron. You have iron here. Fe here is iron, so negative 0.44. Again, so I'm looking at magnesium and chromium, right? So magnesium would be, again, it would be above. Let's see if I find magnesium here. I don't think magnesium is here actually, but is chromium here? Chromium is right below it. So negative 0.44, which means chromium will get oxidized first before iron does. But however, copper is above it, right? So copper is above it in terms of the standard reduction potential, right? So therefore, if copper is above it, then iron is going to get oxidized first before copper does, right? Basically, that's the order here. I don't think magnesium is on this, but I'm pretty sure the magnesium, the standard reduction potential is lower than iron here. So it would be able to protect it against corrosion. Therefore, this solution here is correct. Solution here is correct. And I wish that you included the reduction potential tables to help compare the three metals together to figure out which metal oxidizes / corrodes. Okay, so that's going to be my video for today. Again, thank you so much for watching. Again, I hope I answered your question, Damon, Zachary. Thank you for tuning in again. Again, what I'm going to do is, again, my name is Joey. I'm going to be basically streaming math from Monday, Wednesdays, and Fridays for you to follow along, and chemistries on Tuesdays and Thursdays. So if you're free at that time, definitely take a look on the YouTube channel. Again, it's youtube.com/OneClass. Again, my name is Joey. I hope you learned something through this 1 hour of me kind of verifying solutions. Yeah, that's basically about it. Again, thank you so much for watching. Important things, again, is to stay safe, stay healthy, and again, as always, thank you for watching. Take care.